which was much smaller, it wasn't national, it was just a particular district, there were a series of meetings and consent and that whole process before communities were sort of brought into the program. And in our program, there was a public health technician who was involved in all the schools and distributing the drugs. But in the national program, to save on cost, they just train teachers, and that's seen as a much more cost-effective way of doing it. The only real risk with these drugs is, in a small number of cases, about 10% of cases, there's some side effects. And the side effects are typically, if you have a lot of worms and the drugs are being affected, you have abdominal pain. I mean, basically, the worms are being killed off, and kids will get diarrhea. And in about 2 or 3% of kids, maybe 2% in our data, kids vomit. So there's just all this gastrointestinal discomfort because the drugs are killing the worms. But it's basically transient. It's something that in a matter of hours passes. The downside of it, of course, is if you're a little kid, it's a very traumatic thing to be vomiting, and it happens at the school, so the other kids can see it. So, in the actual data, it's a few percent of cases, but a much higher proportion of kids will have seen some side effects because someone in their class would have had to run to the bathroom or would have had abdominal pain. And in very extreme cases, I think the teachers are trained to try to refer kids to local clinics if something is going awry. But they're seen as very safe drugs. Yeah, Radhika.
Does the deworming in schools decrease like a household's worming incidence? Just because not enough kids go back home and the parents have worming issues, then wouldn't it increase the
Yeah, so there's another paper related to this. There's a whole economics of worms. Little did you know. Things are just getting weirder and weirder around here. But this is actually a former student of mine, Owen Ozier, who's at the World Bank now, and he studied exactly this issue. What happens in these communities to young kids, basically infants, in households where the community was getting deworming, to try to measure the externality. And he finds, A, if you were a young kid when deworming was administered, you show some gains later on. And I'll talk about the research design, the treatment and control way he gets to that. And he also finds if you had an older sibling, you have particularly strong effects. So that suggests there's a couple explanations consistent with that, but one is your story that you're getting more of this almost direct benefit, that in your own compound, there's sort of less reinfection going on. So, yeah. So in the case of countries with national programs like Kenya, there have been some very large statewide programs in India with tens of millions of kids treated. Then they're really just distributed through the government mechanisms, and the data we have suggests the vast majority of kids get the drugs through those sort of large-scale programs. Now, before there were those large-scale programs, even before the district-level program in Kenya that I'll talk about, very few people bought them privately. So 5% of people would buy deworming drugs. Again, relative to malaria or HIV or these other problems, deworming is a smaller concern, and it just wasn't something that households were sort of investing in terms of their health. But they were available. So pharmacies in many East African countries, the ones I'm familiar with, have deworming drugs. It's just they're not that much in demand. Okay. So great. So what's the impact of worm infections on education? This is going to be our question. This is going to try to hone in on that channel. Remember we were saying, how does poor health affect income? Well, education is this interesting channel because if it affects you in childhood, it can have very long-lasting consequences. We're going to spend the next kind of lecture and a half, maybe 2 lectures, just trying to understand this question. And to kind of get your guys thinking to start with, let's do another clicker question here with which of the following 3 outcomes do you think is most impacted by deworming? I told you about the disease, the anemia, the nutritional consequences. There are actually different types of educational outcomes that educators care about. They care about test scores, of course. They care about school attendance. They care about graduation. So I just want to get your guys' guess. Now, you may have already read the chapter, read the paper. You may have already memorized all the tables. This will be easy for you in that case because there's one of these that really comes out very strongly in the data. But let's get everybody's kind of baseline view. All right, let's take a look. So, okay, you guys did the reading already. Okay, so school attendance, which actually is going to be the main channel, but some say academic test scores and graduation or all 3. So, we're going to get to the precise results, but you guys are on the right track there. Okay, so what is the impact? What we know before getting into any experimental variation or kind of fancy econometrics, if we just look in data, in African data, we get data on poor health outcomes, like having lots of worm infections, and educational outcomes, they are correlated. So it's just the kind of thing we talked about in lecture last time. Sicker kids do worse in school. But as we discussed last time, it's kind of hard to interpret that relationship. And as you recall from last time, it could be that the poor health is affecting their education, it could be that their education is affecting their health, it could be both, or there could be some other factor that affects both of these. So now that we're talking, last time we talked about 5 or 6 very general omitted variables. In this particular case, think of a rural Kenyan school. If we were looking for omitted variables, confounders that might explain this relationship, what would be a pretty good, kind of leading explanation of a C factor here that both leads to poor health and poor education? What would you look at? So explain how nutrition link them.
looking at well-fed men you aren't functional at school. If you're also eating like low-calorie food that maybe isn't like kept well or is like exposed to a lot of germs, then
yeah, so if you're undernourished, you can't fight off disease, you may get sick, and if you're undernourished, you can't concentrate and do well in school. So nutrition could be, nutritional consumption, caloric consumption, all the different micronutrients, macronutrients, all these things can affect our body in a lot of ways. Maybe that's the C factor. Maybe it's nutrition. What's another one? Okay, so explain how that would work. So maybe very isolated areas just don't have the infrastructure. It could be transport. It could be certain areas have bad schools and don't have clinics or something, right? So they just lack infrastructure, and that kind of explains its correlation. These are just isolated areas without public investment. So they don't have good health, they don't have good education. Maybe there's no link between the two. There's just areas with really good schools and clinics and areas with really bad schools and clinics, and outcomes look different in those different places. Yeah.
Maybe income could as well, because say a poor family might have their kids help out and be able to do extra work and everything, and that might make them school and like where they're not making sense.
That's right. And that's the income explanation, or sort of socioeconomic status, the kind of broader umbrella, is one that people often reach to first here and saying, if you're from a poor family, you just have fewer opportunities to learn, to get good health care, you have less educational stimulation. So for those reasons, you may look worse on both of these dimensions. So that'll be another. There's another hand up in the back. Is there another hand up in the back? Okay. So those are all very good potential explanations and all very plausible. Now, it's interesting when you look at income, the income story may tie into the story on nutrition, because maybe if I'm poor, I can't afford good food or enough food, and that leads to the sort of health and educational consequences that were raised before. And the point before about infrastructure may be more of a population level outcome, but maybe very poor areas can't invest in schools or clinics, right? So underlying this is resources and income could kind of explain both. So let's get to some econometrics and try to formalize this a little bit. So what do we have up here? This is a regression equation. Hopefully it looks familiar to you. if you have no idea what something like this could even mean, then we just have to talk about bolstering your statistics and your econometrics. But what do I have in mind here? Imagine Y is the educational outcome of interest. So here, let's say school attendance. That's going to be one of our key outcomes. W is some indicator variable, 0, 1 variable, for having worm infections. So we're interested in whether kids with worm infections have worse educational outcomes. We're very interested in that coefficient B. And the hypothesis is that B is negative. If I have worm infections, I have less school attendance. That's what we're really interested in. And finally, there's another child characteristic, and this is the sort of household poverty story, but again, that may tie into nutrition infrastructure. There's a lot of things poverty does. But let's just imagine that that's a really key determinant of school attendance. That if you're poor, your family can't afford to send you to school, or for some other reason you don't go to school. The last term there, E, is the white noise error term that everybody loves. Okay, so the coefficients to be estimated are A, B, and D. These are the key parameters. B tells us how worm infections affect school attendance. D tells us how poverty affects school attendance. So again, we would think that if X is poverty, imagine it's an indicator variable for being poor, then D would be negative. Probably poor kids have fewer educational opportunities or less educational success. Okay? Again, the white noise error term there means the expectation of this error term, on average, the error term is 0. And in terms of notation here, I is a person in the population. Let's say there are n people. So this is our sample size, I from 1 to n. Now, another way you could look at the data, and this is actually what's going to be on the problem set, is you could look not just at person averages, you could look at household averages, you could look at community averages, school averages, regional averages, and then I would denote the household or the region of the school. You could take averages, and maybe in some areas there are more worm infections than others. So on the problem set, it's actually going to be school-level data. You're going to have school-level averages for all the schools in the deworming study. Yeah, Martin. Yeah, I'm not going to pin it down so much, but let's just think of when X equals 1 here, let's just imagine that you're poorer, you have worse nutrition, you have lower socioeconomic status, you have less opportunities. This sort of bundle of socioeconomic status variables that are combined in X. And I'm going to show you that X is going to be kind of an omitted variable here. Maybe it's kind of hard to understand all these dimensions of socioeconomic status or measure them. So it's hard to pin down exactly what's important here. It doesn't really matter in the econometrics. We could leave that continuous or as a dummy. I was saying it's a dummy just for simplicity. So let's just imagine it's 0 or 1, just for simplicity. But it could be continuous. W could be continuous here. I'm going to show you everything with dummy variables because then all the equations just boil down to very simple differences in like parameters. And but everything goes through with continuous data. And in fact, in the problem set, you're going to have the treatment. We're going to talk about treatment variables in a second. The treatment variable is going to be a dummy variable in the problem set, but the other variables are going to be continuous variables. And it doesn't matter. It's just the algebra is simpler this way. Okay, any other questions on this? Okay, so there we go. So W is our indicator for having worms. And again, I told you that what really matters with worms is having very heavy worm infections. So again, it doesn't really matter. We're just looking at things in the abstract, but maybe the kind of right indicator variable is having a serious infection. And parasitologists can measure that. They measure it in a really nasty way. They collect fecal samples and they count the number of eggs per millimeter cubed. I guess you got to do it, But they basically have classified different densities of worm eggs into different intensities of infection. If there's tons of worm eggs, it's because you have a lot of worms in your body. So there's actually like quantitative data, and we have that in our study, of who has the serious infections and who has the light infections. So maybe if you only have one worm in your intestine, it doesn't really matter. But if you have one of these serious infections, that's what matters. In which case, you would think, this is an indicator for having one of these heavy infections. Okay. So let's just go through and try to understand this equation. Everybody should be familiar with this. We're going to think of things in terms of expectations. So you guys are familiar with what an expectation is. It's like a population average. Sort of imagine there's some variability out there. On average, across all those observations, what is the average for y sub I? That's the expectation, right? It's the mean of this population. And let's imagine the mean, the expectation, conditional on the vertical line, w equal to 1 and x equal to 1. So w equal to 1 is you have serious worm infections. X equal to 1 is you're poor. So what does that regression equation look like when w is 1 and x equal to 1? Well, you can work the expectation operator through. This is basically just this simple sort of linear equation, linearly separable regression equation. And the expectation of y is just the expectation of each of the terms. The constant terms move out of the expectation. Those are just scalars. They're not random variables. There's no expectation for them. It's just a scalar. So what does that expression equal right there? Can you just kind of go through an eyeball? What is yeah? Y2. You're very close, but you're forgetting the coefficient estimates there. Great. And what about the last term, the error term? That's right. So if we have a properly specified model, this was the right model, then just by definition, that error term is orthogonal, meaning it's independent of these other terms. Okay? So that's where we're at. It's a plus b plus d. Everybody can see how we go through that. Basically, we're going to go through and find these expectations for different subgroups, and then we're going to compare them. And why do we care about comparing them? We want to compare the people with worms to the people without worms. So we have to go through this little algebra. Okay, the second one. What if you have, w equals 1, you have serious worm infections, but you're not poor. X equals 0. Now it's just a plus b. There's no d term because x equals 0. So now you can see why I did things in terms of indicator variables because terms just drop out. It becomes a little bit simpler. For people without worm infections, but who are poor, group 3, it's a plus d. This is already really repetitive. Let's just go through it one time. And for the fourth group, these are people without worm infections who are not poor. It's just a. It's just a constant term. So a has this simple interpretation. A is like average school attendance for the people who are not sick and who are not poor. Okay, and remember before, we were thinking of B and D as probably being negative, so probably the average attendance for those groups is less than A. Any questions? Am I going a little too fast, a little too slow? Just right, perfect. Any questions? Okay, so this is our reality when we have all the data. We have W and we have X. We're going to be focusing on omitted variables here. When we can measure everything, and we want to understand the treatment effect, it's not too hard, right? We just kind of have all the data. We can take the, I can take the difference between, group 2 and group 4 to get B. I can take the difference between group 1 and group 3 to get B. I just take these simple differences and I get B because I have all the data. Yeah. Oh, no. Okay. Now, that was the nice case. In reality, as we discussed today, there's a couple of different omitted variables or confounders that are possible. Last time we talked about like 5 other ones. What if we can't measure all the potential omitted variables? What if, let's just say in an extreme case, we just don't measure X. We just know if you're sick or you're healthy. W equals 1, W equals 0, and we have Y. We have school attendance. When we take all these differences, what are we going to come up with? Well, it's going to be a little bit different. So when we start taking expectations here, and you can stare at that equation for a second, the expectation of Y for those who are sick, well, it's still A plus B. We know that. But now we have this different term here. We have the expectation of poverty, average poverty, among sick kids. That's in there now. And we have average poverty, x, among healthy kids, W equals 0. So why is that extra term potentially an issue for us? What are we concerned about? Yeah. Okay, so if, in this first term, if there's a higher probability you're poor when you have worms, and a lower probability that you're poor when you don't have worms, the difference between those two terms is going to kind of contaminate our interpretation of this difference. Now the difference between the healthy and the sick is the combination of the difference between being healthy and sick and the difference between being rich and poor. They're both in there, and there's just no way we can difference that out because we don't measure x, or we can't measure whatever other confounder or omitted variable we're worried about. So this formulation gives us just a very simple expression for the omitted variable bias term. So now when we take this difference, we get what we want, we get b, that's what we want, and we get this other term, b times the difference in the poverty rate among the healthy and the sick. If you read the newspaper and you read whatever interpretations given to data in popular life, I think most people are kind of aware of this problem that when you compare two populations, they differ in lots of ways. It's not as simple as comparing the healthy and sick. Healthy and sick differ in lots of ways. So what we have is the true effect plus the omitted variable bias term. And if you look at this, you say, well, we can kind of quantify that. No, we can't because we don't know what x is. So we're estimating just that difference, and it's a combined effect of these two things. This is the bias term. Let me pause, see if there's questions on that. Yeah. To use instrumental variables? We're going to come to that in a few weeks. That's going to be one of our solutions. So we're going to start by trying to solve this problem with a randomized experiment, and then we're going to get into instrumental variables, regression discontinuity, this term. But in modern applied econometrics, when people see this problem and they don't have access to a randomized experiment, they're going to try to find instrumental variables. We'll talk a lot about them. So that's kind of like the response that economists today would give, or really social scientists would give, because a lot of political scientists are using instrumental variables now, other researchers, to this problem. So we're going to come to that in a few weeks, and that's sort of the direction we're going in. Okay, there's another way to write this expression. This is maybe what you saw in your econometrics class. Usually people say, there's a correlation, there's sort of a correlation between the error term and a variable of interest. That's the way they talk about omitted variables. So how can we put what we just had up there in terms of this error term? So there's a very straightforward way to do it. When we're running the regression, so if you go back to the previous slide, sorry for a sec, that average difference between, look at equation 2, the average difference between the sick, W equals 1, and the healthy, W equals 0, the other way to write that is with this equation up here, equation 1 prime. I'm going to take the average difference between the sick and the healthy. I'm going to call that coefficient estimate B, my coefficient estimate of interest. But keep in mind the following. If the true regression equation has the dx term, then basically the dx term is in your error term. So now, it's just another, what we're doing here is basically just algebra. If we write things in terms of this new error term u, which is the true white noise error term plus the omitted variable, then this is the more common expression you'll see for what an omitted variable bias term looks like. It's the true effect plus the sort of difference in, the average difference in the error term with respect to w here. In other words, there's some correlation between the error term and your key explanatory variable. But the reason why is we think there's some actual omitted variable in that error term. If the error term were truly white noise, you wouldn't have this kind of correlation. It's just because it's not white noise. There's something else in there. Have people seen formulations of omitted variable bias similar to this in your econometrics class or statistics class? This is the usual kind of way to express it more or less. Usually it's expressed with continuous variables, and I just boiled it down here to the dummies to be simpler, but everything, of course, goes through a continuous variable. Fantastic. Okay, how can we solve this problem? Let me ask you guys, when can we solve this problem? How can we solve this problem? The issue of instrumental variables came up as a solution. I'm going to kind of skip over that for now. We're going to come back to it in a few weeks. What are some other potential solutions people can think of? Okay, the simplest solution would be just to get information on x. If we actually felt like we knew what x was, we should go out and collect our own data and gather data on x. Or maybe there's 4 or 5 potential omitted variables. We should go out, collect data on exactly those omitted variables. And even if we haven't captured all the omitted variables, if we've captured a lot of them, or the leading ones, or important ones, every single additional one we include as a control in our regression, we're going to be reducing omitted variable bias. Maybe it won't go to 0, but it'll get better. That bias term is going to get smaller. So this is what a lot of researchers do. A lot of us in development economics run our own surveys, and we spend huge amounts of our time and energy trying to get the best possible data to solve this problem. The problem with it is you can't always get x because you don't always know what x is. Some x's are also very hard to measure. So we think, in some cases, the omitted variable has something to do with someone's maybe personality, their attitudes. We can try to collect that, and certainly our surveys help us collect that kind of data, but it's harder to collect than something simple like how much education do you have. That's a pretty easy one to collect, although not trivial. So it's hard to collect a lot of good x's. It's expensive, and sometimes we have existing data sets that just don't have the data we need. So we just don't have x. Maybe it was a survey collected three years ago or 10 years ago. We really want to analyze it. And maybe there's 10 plausible omitted variables, and they just don't have data on them. So we can't use this approach. This isn't going to help us. The second way this problem is not a problem is if you don't have omitted variable bias. Now, why am I saying this? It sounds stupid. I'm just trying to go through the different terms in the regression equation. So if remember there was that dx term, okay, if we have x, we're fine. If d equals 0, we're fine too. So for some reason, there's no omitted variable bias, we're fine. So usually we think there probably is omitted variable bias, but if there isn't, we're home free. Okay? Basically, if d is 0, that second term just goes away.